the sine of theta, which means it's W, the sine of 30, which will be a half of W. But then it's not only FG parallel that's acting downwards in this trade. So A is out. Then W plus F wouldn't make sense. W minus F still doesn't make sense, because remember they have to be equal to each other, which means if there's any subtraction, there's an addition that's taking place, everything must just reduce to a 0. And the last one, W sine 30, that is only representing the FG parallel. So this question doesn't seem to have any correct option. None of the options are correct for 1.1. Let's look at 1.2. A box M is being pushed horizontally at constant velocity on a rough surface by a force F. Okay, so we have the arrows that are indicating the directions. Okay, if the force F that is acting decreases, then what happens? If no force acting on the body decreases. Okay, that sounds correct. Velocity of the box decreases. That's automatic, because since the force is going to decrease, which means even the rate at which it's moving will also decrease. Acceleration increases. The acceleration will instead decrease. The normal force increases. So option A and B, I'll go for option B, which is kind of straightforward. The velocity of the box will decrease. Then 1.3, the ball is dropped from the height of the height. After it falls, it reaches a velocity. Which of the following is correct? After it falls 3 meters. Now remember, this is VP. Okay. Okay, so since it's vertical projectile motion, we know that our V initial is a 0, since the ball was just dropped. Now we know that the delta Y is a 5 meter. The acceleration due to gravity is 9.8 meters per second. Okay. Now after it has fallen 2 meters, it reaches a velocity. They want us to get a statement for 3 meters. Telling us at 3 meters, the velocity is going to be this. I don't know that. Let me first find what the speed is at 2 meters and then at 3. So if I use the VF is equal to the VI, I'll use the AT or the GT. So RV final is what I'm looking for. Initially 0 plus 9.8. But this doesn't have time, which means not going to make sense. There's no time involved. We don't have anything to do with time. How about I use the V squared one? It makes sense, yes. VF squared is equal to VI squared plus 2as or delta X or delta Y. Then, so our VF squared, we initially said is a 0. 2 times 9.8 times 3. Okay, so when I get to my calculator, 2 times 9.8 is going to be 19.6. Then 19.6 times 3 is giving me 58.8. Then when I find the square root of the answer, gives me 7.66. So the velocity after 3 seconds, after 3 meters, has to be 7.6. Telling us that the velocity is 3, that is out. The acceleration is 3 now, then the acceleration must be 9.8. which means option C makes a lot of sense. We don't even need to look at it because the ball is right, which is also wrong. Okay, then 1.4. In which of the following rows does the type of collision match with the total momentum as well as the kinetic energy? So with elastic collision, momentum is conserved, kinetic energy is not conserved. This is right. Inelastic, momentum is conserved, that's correct. Kinetic energy is not conserved. So I think it has to be B. Because in B, we can see that everything is correct for the momentum and the kinetic energy. Then 1.5. A block slides over the rough horizontal surface and eventually stops after 1.5 meters. Which of the following is false for the movement of the block? Okay. Are telling us that the net work done when the block decreases its kinetic energy. This is correct. Because we know from the work energy theory that the net work done is equal to the change in the kinetic energy, the EK. Okay. Now, when a block is getting slow or eventually stops, you know that the final velocity will be 0. And if we use the 0 minus the initial, which means we're going to get a negative kind of work done, which means it decreases the kinetic energy, which is true. The net work done on the block decreases its mechanical. That is also true when you look at the conservation of energy. Then the net work is negative, which is true, and then the block is slowing down, which is also true. Yeah. So which means all the options are correct. Just choose one. 1.6. The diagram below shows the absorption spectrum of an element from hypothetical stars A up to B, as observed from the Earth. Which star is moving away from the Earth with the highest velocity? So from B is equal to F lambda. So if the velocity is high, then we expect the wavelength to also be long. Okay. So when you look at the lines, the red shifting and the blue shifting, I think the best option has to be A, because we can see a bigger difference within the blue shift, and we have the smallest distance within the red shift. So option A is the best. 1.7, the diagram below, we have 2-point charges, which is the +5 coulomb, and then the -4 coulomb at a distance of x meters from point P. That's which means they are equidistant. Then they want the net electric flow in terms of P. So what we can see is that if I look at the Q1 and the P, okay, so Q1 is positive, and this is a positive charge, positive point. Okay, so positive charges, they will repel each other. Okay, so in other words, the force that is acting on P is going to be to the right. Okay, so which means if I'm looking for my electric field, KQ over R squared, it's going to be the K, which is a constant, the R, which is also a constant with X, and then this Q, which is now the 5 to the east. Okay, then let me look at P and the Q2. Okay, P and the Q2, this negative, this is positive. So they're going to be attraction, which means the force still acting on E. So then P is to the right. So which means my E is KQ over R squared. The Q is a 4. Okay. So if it's a 4 to the east, which means the net is going to be this 5 plus the 4, which must give me 9E to the right. Okay, 9E to the right, which is E. Okay, then 1.8. 1.8, we have a circuit below, which is set up. The reading of the EMF is 9. There's internal resistance of 0.2. And then the ammeter reading is 1.8. So which of the following is correct when 1 coulomb charge flows in the circuit? So 1 coulomb charge is more like the energy that is moving around over. Okay, so when we look at this, we have some sort of internal resistance within the battery. Okay, so 1 coulomb charge flow. Let's see, they're telling us that 9 is the potential difference across the resistance. So if the current is 1.8, okay, now that V is going to be but we know this EMF is I plus I small r. They give us the internal resistance as 0.2. This what is 0.2 times 1.8. 0.2 times 1.8. That gives me 0.6. When I subtract that from the 9, 0.36, I'm getting 8.64. So 8.64. So the first option is wrong. Doesn't make sense. And then 9 joules of energy is dissipated within the resistor. So when you look at the power, you know that power is current times the voltage. Okay. So the voltage is 8.64. The current is 1.8. So 8.64 times 1.8, I'm getting 15.552. So this is also wrong. And then 8.64 amps is flowing the circuit, and that's wrong. Okay. That is wrong. And then 8.64 joules of energy is dissipated in the resistor. And that would make no sense. That would make no sense. Then 1.9, an EMF and being used across a stationary coil gap, a stationary magnetic field. Now, using more turns in the coil, this can only increase. Changing the magnetic field, yes, that's very correct. Then 1.10, we have diagram below shows the energy levels of an electron. The energy needed to excite an electron in the ground state. The energy needed to excite an electron in the ground state to the first level. Okay, so this question, remember from the scope that we have, this was scrapped out. This was scrapped out. But what would be the answer? Energy needed to excite the electron from the ground state to get to. I'm not even going to think of this. Let's move on to question number 2. Okay, so 2 blocks are attached to each other. They are like next tense was 3 moving over the frictionless pulley as shown in the diagram below. So we have a slot AB with 50 degrees, and then the slope is you're serving 30 degrees. Okay, then they want us to stretch Newton's second law of motion. Okay. So we say that when kinetic force acts on a body or acts on an object, the object will accelerate in the direction of the force, and then this acceleration is directly proportional. It's directly proportional to the force, and inversely proportional, to the mass. Just as straight as that. Then they're telling us that the coefficient of kinetic friction between the slope BC is 0.2. They need us to draw the direct line at M2. So when you look at M2, one, we're going to have the FG parallel moving that direction. We're going to have the tension of the string. We expect to also have the normal force upwards. Let me just put it in. The normal force secting downwards, and then the FG perpendicular in this sort of direction. So what I'll do, I'll say this is my F normal. This is my FG parallel. And that is my tension. And then this is going to be the weight. I'm going to put the FG perpendicular. Is there friction? Yes. That means there's also another friction first. Okay. So we have around about 5 forces. It's the force. Then they want us to calculate the magnitude of the acceleration of the system. Okay, so for us to get the acceleration of the system, it's either we look at the two combined bodies at once. That will give us an option of eliminating the tension. Or we just look at the second law of motion of the F net is equal to MA, so that we can get our net force and then the acceleration in return. I don't know which option will be bigger and better. Let me just, what is happening with slope AB? The friction is small, which means there's no friction. Yeah, we can do that. I can do that. Let me try to look at the entire body. Just make sense. Makes sense, won't make sense. Let me look at body A, the M1. So when I look at M1, if I assume that this system is going to move in this sort of direction, which means the tension here must be greater. It's going to be F net is equal to MA. Okay. Then that's going to be the tension minus. Let's just put it aside. So we're saying the tension minus the FG parallel must give us the MA. Okay, we don't know the tension, but we know that the MG is going to be MG sine of theta Let me just substitute. So we know that the mass is 12 kgs. So that's a 12 times 9.8. And then the sine of 50 is equal to 12. Now, for that my equation number 1. Then when I look at M2, consider M2. So the FG parallel is going to be greater. So I have my definitive bit is equal to MA, which means my FG parallel minus the frictional force minus the tension must give me the MA. Okay, so what is the mass of this body? It's 70. 70. With the frictional force as well. So that is 70 times 9.8. The sine of it. That's correct. Minus the frictional force. Remember, frictional force is always given as the coefficient times the normal force, which normal force is mg cos of the angle of inclination. So I'm just going to substitute that. So minus the 0.2 times 70 times 9.8. The cos of 30 minus the tension, it must give me 70 times the acceleration. Okay, then since I'm not interested in getting the tension, I can look at equation number 1 and make tension the subject. Okay, so my tension will be 12A plus 12 times 9.8 sine of 50, getting 90.0868. Okay, then I'm going to get this and replace it where I see the T. Okay. Then this is going to be 70 times 9.8 sine of 30, I'm getting 343 minus the frictional force 0.2 times 70 times 9.8 cos of 30, that gives me 118.819. I'll 3 decimals. That's for the sake of accuracy. Then I'm replacing the T, which is 12A plus the 90.0868. We said it must give us 78. So when you subtract that, 3, 4, now let me just open the brackets first and then 343 minus 118.819. That gives me 234.181. So minus 12A minus the 90.0868 must give us 78. So I can move this 12A to that side. That's going to give me 82A. And then 224.181 minus 90.0868. Getting 134.0914. Then I'll divide both sides by 82. So over 82 over 82. Okay. Then I'm getting 1.635, which is approximately 1.64 meters per second squared. I think this makes some bit of sense. It's acceleration, not so big and not so small. Okay, so that is the answer 1.64 meters per second squared for 8 months. Okay. Then 2.3, they're telling us if the angle of BC is decreased. Okay, to 20. Will the frictional force between the block and the slot increase, decrease, or remain the same? We don't need yes, I not skip anything. Will it decrease or increase? So in this case, remember our frictional force. We said it's mu mg cos of theta. We just need to look at what is the cos of 20, okay, and then the cos of 13. Okay, so if the angle is at 30, the frictional force becomes small. And when the angle is reduced to 20, the frictional force becomes big. Because in this case, to easily kind of drop or slope downwards. And then when it's a 20 slide, you're making it difficult for the block to slide below the incline. So in this case, we're going to say the frictional force will increase. And what will be the explanation? We know that frictional force is directly proportional to the normal force. Okay, so if the inclination is small, which means the normal force is going to be big. Okay, so I think that's enough. It's increasing because the frictional force is directly proportional to the normal force. Hence, the frictional force increases. The frictional force increases. Okay, guys, that's question number 2. Question number 3. I'm telling us we have a 25 round ball that's thrown vertically upwards. The ball leaves the hand 1.3 meters above the ground with the initial velocity of 7.27. On its way down, the ball bounces off the balcony at 3 meters per second before being caught at its maximum height after the bounce, ignoring friction and any horizontal motion. What's a projectile? Okay. So we know that a projectile is just a body that's just under. For someone as what is straightforward, what is a projectile. So a body that's under the influence of the acceleration due to gravity. Okay. Right. Okay, so we're saying a projectile is an object. Okay. An object with, let's say, an initial velocity, and then moves under the influence of the acceleration due to gravity. Remember, I said there's a difference between the free fall and the projectile. So with the projectile, you must give the object some sort of initial velocity. You must give it a push. You must keep static before acceleration due to gravity can take place. Okay. Then third question, they want us to calculate the maximum height above the ground that the ball will reach after it was thrown in the air. Okay, so they want us to do this. So what do we know about the initial velocity? We told us that the VI is 7.27 meters per second. They want the maximum height. Okay, so we know that at maximum height, the V final has to be 0. Okay, then we can use the V squared. So VF squared is equal to VI squared. plus 2. Here you can see delta y. Okay, since the ball was thrown upwards, I'm going to check my upward negative and my downward positive. So this is a 0 squared. Is equal to VI, which is 7.27 squared, plus 2. Our is now negative 9.8 times delta y. So 7.27 squared is giving me 52. 857 is equal to 19.61. And so this one will be negative 19.6, but when I transpose it, I'll get a positive. Then I'll divide both sides by 19.6. We're getting the 2.6965, which is like approximately 2.7. So which means from there up to there is 2.7. But the question was asking us from the ground. Remember, this ball was thrown 1.3 meters above the ground. So it will be the 2.7 plus the 1.3, which is approximately 4 meters. Okay. So it's approximately 4 meters. If I didn't round off, it's going to be 2.697. And then I'll put my 1.3, which is 3.997. Which is approximately 4 meters. Okay, then 3.2, they want us to get the time that it takes until it bounces off the platform for the first time. So we know that it goes up. And then it bounces. It bounces off with 3 meters per second. Okay. From the time it takes until it moves. So from the point of projection, up until it's there. What do you think? That's the point. So we could use the V prime is equal to V5 plus 18. Okay, so this 3 meters. When it's so it bounces off the bottom, it goes in brackets. So are we going to assume that it's a 3 meters per second? Will that make sense? No, it doesn't. It will not make sense. Because what I can do is if now the velocity of this mass is 0. I don't know the velocity of this point, because that is after the bounds, which is not going to make sense. It's not going to make sense. But I can get the distance. Since I know from there, this maximum height up to below is 4 meters, I can subtract this 3.2. So at the distance I have is the displacement. Yeah, makes sense. So let's see. So which means my delta one. Let me just put this. Okay, so saying my delta y is going to be 4 minus the 3.2, which is 0.8 meters. Okay, so that's our displacement. Our initial velocity, since it was now maximum, is going to be 0. Because now I'm looking at the second journey. Okay, from maximum, now dropping down. Okay, that is true. I need time. and time. So the displacement should make sense that second of the delta y is equal to VI2 plus a half H squared. Yeah, it would 0.8. So that's going to die out to be just a 0. This is a half times 9.8 and T squared. Taking the 9.8 to be positive since now it's the second term that is dropping down. Okay. So this is going to be 4.9 T squared is equal to 0.8. Divide both sides by 4.9 and then find the square root of the answer. What making sense, which is my answer, which is 0.4, yeah. What other information do we know about time? So let's look at the question. Let's look at the question. Because that 0.4 is just for this root, which is very correct. The question has the total time taken from the top. Oops. But then we have to do it back in the class using the change in y. So then what's going to be the displacement? Well, 1.3 up to that. And so that was 2.7. So it means we can use the 2.7. 4 minus 1.3 plus 2.7. That's very correct. It's 2.7 and then the time as well. So 2.7 is equal to now initial, which was 1.3. There's 1.32. Now I'm subtracting a half times 9.8 T squared. Okay, so when I use my quadratic formula, 1.3 minus, I'm just going to say 4.9. That makes sense. Maybe there's something really wrong. See, let's see. So this was a 0.4, this and we need the time from the point of projection to the maximum. Well, nice of the conclusion. Use that define equal to the initial plus A2. Yeah. So this final is a 0. Initial is 1.3. Now minus 9.6, 1.82. So which means our T is going to be 1.3 over the 9.8. 1.3 divided by 9.8, which is 0.132. Okay. So then I can add the 0.4 plus the 0.3. So that's going to be 0.5. Why are we using 1.3 again? It's 7.27. So 7.27 divided by 9.3 is measured up in 7.4. So it has to be 0.74 plus the 0.4. 0.74. That gives me 0.7. 0.74 plus 0.4. That's 1.14. 1.14 seconds. Yeah. Then 0.3, they want us to stretch the graph of displacement. Before the interaction. We're using the ground as a reference point in the line. Now, remember with the different graphs is the displacement. So how is the displacement? Smaller position. Okay. So when here is the displacement in meters, this is the time in seconds. Okay, so what we shall notice is that this ball is going to start at a height of 1.3 meters. Then it will go up, reach a maximum at a height of 4 meters. That's what we said. Then it will come down after a certain time. It will bounce for that time that it is calculated the 1.14. Then it will bounce up again to another height, which is below the maximum height. So something of the nature will work perfectly. Just make it up. So something like that. After that, and that. So this we don't need to know it. But before we need to, for the sake, we need the max, the height from which the ball was released, the 1.3. That is in the 3 cage. The maximum height, which is a 4. The height of the balcony, that's the height of the balcony, it's 3.2. Which is that. And then the time it takes to bounce down. So something that can reach out would guarantee you 5 minutes. Then question number 4, when a ball hits and bounces off the surface, it exerts a force on the surface. So some group of learners investigated how this force varies over time as the ball hits the force sensor and bounces up. We use the 50 grams of force from a height of 1.5 meters above the sensor. Okay. And then the following part is derived. And then the first question comes, asking us to define impulse. Okay, so when we are defining impulse, the definition is that it's the product of the net force that is acting on an object and then the time. The net force acting on an object, it's time. Okay, so we say product of the net force acting on an object and the time that it takes. Okay. Now, avoid using the change in momentum kind of terminology because that is more like an application. It's not a definition of impulse. Then they want us to use the information in the graph to determine the magnitude of the impulse as the ball hits and bounces off the sensor. Okay, now, remember we said impulse is the product of force and the time. So we are indirectly being asked to determine the area of this triangle. So we know that area of the triangle is given as a half times the base times the height. So that's a half. Our base is 15. So from 0 up to 15. And then our height is going to be 64,130. Okay, so a half times 15 times 64,130 is giving me 480,98. 480,98. But remember, this time is in milliseconds. So which means I have to divide by 1,000. This means I have the 0.481 differences. Time as in milliseconds, so divide by 1,000 or multiply by 10 to the negative 9. Then 4.3, can we state the magnitude and direction of the change in momentum of the ball? So what we can see is when the change in momentum, mass, or change in momentum is the same as impulse. We don't need to go back to the mass and the velocity. So this 0.48, since it's positive, we're going to take it to the upwards. Okay. But then, what is the question asking for? The magnitude and direction. So 0.481 newtons upwards. It's upwards, positive. All right, then if the velocity of the ball just before it hits the first sensor is this downwards, can we calculate the velocity with which it bounces off the sensor? So then you can use the F net formula. F net times delta T, that's the impulse now, is equal to the change in momentum. What is the question asking for? Calculate the velocity with which it will bounce up. So it is M, V final minus V initial is equal to F net and delta T. So we know that the F net times delta T will give us that 0.48 volts, which is the impulse. Okay. So shall say 0.481 is equal to the mass, is the equals 25 grams. 25 of it is 50. It's 50 grams. So convert the grams to kilograms. That's going to be 0.05 kilograms. Divide by 1,000. I'll open this. The final minus the initial, which is 5.14. I'll start by dividing both sides by 0.05. So 0.481 divided by 0.05, I'm getting 9.62 is equal to V final minus 5.14. Then I'll move this 5 to that side, which will be 8. My sense correct, because the final is moving upwards, and then the initial is moving downwards. So it's a minus, that's a plus, so which means I'm going to subtract. So 9.62 minus 5.14. That's giving me 4.2 meters per second. Okay, so that's our final. So the final is going to act upwards. Then 4.5, we've been told that the ball is now replaced with a hard ball. Remember, the previous one was a soft ball. Hard ball of the same size and mass. Will the force on the sensor increase, decrease, or remain the same? Now, with a soft ball, we know that it will tend to take more time in contact with the sensor, whereas with a hard ball to take less time. So in this case, it's going to increase. Why? Because the change in momentum, let's say the hard ball takes more time. Takes more time. It's the soft ball that takes more time. You say the hard ball takes less time to bounce back compared to the soft ball. Okay. So this can be seen under the applications of the air bags of the cars, let's say in car crashes and things like that. So what this means that the force will be inversely proportional to the time, and hence the force will increase if the time is less. That is question number 5. Question number 5, the 5 kg body or box moves up and down at a constant velocity in the force F is applied. Okay. They want us to calculate the magnitude of the force F if the power that is used to move up the box is this. So we know that the average power will be the same as the force applied times the velocity. Okay. So we have our power, we have our velocity. So we're going to have the 57.6 is equal to the velocity, which is 1.2 F. Then divide both sides by 1.2. So 57.6 over 1.2. 57.6 over 1.2 and 18.48 newtons. Okay, so this is the magnitude of the force that's pulling this object. Then they want us to state the work energy theorem. So this tells us that the net work done, okay, the net work done is equal. The net work done, let's say by net force. By the net force is equal to the change in energy, which is equal. Okay, so if that is true, then they were telling us that the box now slides down this. So still, since the velocity is constant, which means even the force is kind of constant. So if the coefficient of the kinetic friction, the thing that is this 0.25, calculate the velocity at point C using the energy principle on it. So it all depends on how you want to approach this question. Remember, at point B, this object or this box will have mechanical energy. Okay. We have mechanical energy, which is a combination of the kinetic as well as the gravitational potential. And then at point C, we're just going to have the EK to be maximum, since there is no height. So the gravitational potential will be a 0. That's my argument. And remember, energy in any sort of system will always be conserved. Energy will always be outside. So what do you think? What do we think? Okay, so saying the work net, W net is equal to the change in kinetic energy, which I will just say EK plus the EP. The change in EK and then the change in EP. So we know that our work done is given as F times the displacement. So we have our power, we have our velocity. So we're going to have the 57.6 is equal to the velocity, which is 1.2 F. Then divide both sides by 1.2. So 57.6 over 1.2. 57.6 over 1.2. And getting 48 newtons. Okay, so this is the magnitude of the force that's pulling this object. Then they want us to state the work energy theorem. So this tells us that the network done, okay, the network done is equal. The network done, let's say by net force. By the net force is equal to the change in energy, which is equal. Okay, so if that is true, then they were telling us that the box now slides down this. So still, since the velocity is constant, which means even the force is kind of constant. So if the coefficient of the kinetic friction between that is this 0.25, calculate the velocity at point C using the energy principle on it. So it all depends on how you want to approach this question. Remember, at point B, this object or this box will have mechanical energy. Okay. You have mechanical energy, which is a combination of the kinetic as well as the gravitational potential. And then at point C, we're just going to have the EK to be maximum, since there is no height. So the gravitational potential will be a 0. That's my argument. And remember, energy in any sort of system will always be conserved. Energy will always be conserved. So what do you think? What do we think? Okay, so saying the work net, W net is equal to the change in kinetic energy, which I will just say EK plus the EP. The change in EK and then the change in EP. So we know that our work done is given as F times the displacement. If displacement can be, let's say, delta X, and then the force of theta, because that will be now the work done by the friction force. This is equal to the change in EK is going to be a half m v final squared minus a half m v initial squared. And then the EP is going to be mgh final. Okay. And then the mgh initial. Something like that. Now we know that the force was 48. But remember, this F is for the frictional force, the work done by the frictional force. Because if you look at the free body diagram of this thing, I don't want to use those things of the free body and the forces and so on. But we can also use that and get the velocity. Okay, so let me stick to this. So we know that the frictional force is mu mg cos of theta. Okay, so our mu was a 0.25. Okay, times now the mass of the body, which is 5 times 9,8 times the cos of 32. Okay, that is just the F. Now the displacement, I do not know it. Okay, I don't know the displacement, but I can get it. How? Since I know this is my H, and then this is my 32, I can use the sign. We know that the sine of 32 is equal to the opposite, which is 1,6 over the hypotenuse, which is BC. So which means BC is going to be 1,6 divided by the sine of 32. What does it give me? It gives me a 3, something. Let me just do that right away. So my displacement, okay, we get to 1,6 over sine of 32. And then we multiplying by the cos of theta, which cos of theta is like cos of 180 since friction is in the negative direction. So when I simplify this, remember this is just the left-hand side. So 0.25, okay, times 5 times 9,8, the cos of 32, okay, times the 16 over the sine of 32, and then the cos of that. I'm getting a 313,665. Okay, but that is negative. Then when I look at the right-hand side, let me look at the B case. It's going to be a half. The mass is 5 into my V final, which I don't know, minus my V initial. What was the V initial? It was 1,2. And then when I look at my EPs, the mass is 5. The gravity is 9,8. The height is 0. Okay. Then I'm subtracting the 5 times 9,8 and then the 1,6. So 5, 9,8 and then the 1,6. So when I simplify this, I'm having 5 over 2 VF squared. This is out. And I open this, what is 1,2 squared times 5 over 2. That's gives me 3,6. So minus 3,6. Then minus 5 times 9,8 times 1,6. I'm getting 78. Okay, so this is what I'm having by my right-hand side. This is what I'm having by my left-hand side. So now it's time for me to compare the two sides. So 5 over 2 VF squared minus, okay, this is 3.6, I'm getting 82. So minus 82 is equal to the 3,13,665. Okay, so 313,665. So 82 multiplying by 2 dividing by 5. I'm getting that. And then I'm getting 9,6. Doesn't make sense for me. Did I do something wrong? We have a visit this and it's, let's see if I did something wrong, something wrong, something. That's afterwards. These are ones. We said 5 times 9.8 times 1.6. That is 72. Okay. The 0 is out. 1.2 squared times 5. We get to 3.6, which is 35. And then we have a half of that. So which means divide that side. Okay. So from to follow through, let me just go back to my previous pattern, which is 0.25 times that. Which is that. So my correspondences are still fine. It's 5 over 2 v squared minus the 8. They divide both sides. Now move the 8 first. Move the 83. Dividing by 2 and dividing by 4. No, it's okay. I'm just going to ignore the sign here. Make it positive. What this is going to be. So it's 313,665 minus 82. Getting the 231,668 is equal to 5 over 2 v squared. And I'm dividing this by 5 over 2. Okay, I'm getting 92. And when I find the square root, I'm getting 9.6. Okay, 9.63 meters per second. All right, then question number 6. They're telling us that in the diagram A, B, C below, the wave patterns are shown for the sound. So this is A, this is B, and then this is C. Can we define the Doppler effect? So we know that the Doppler effect is just the apparent, okay, the apparent change in the frequency that is received by the listener as a result of the change in the velocities and so on. Okay, but alternatively, we could just put it as the apparent change in the frequency or pitch of sound as detected by the listener because of the sound and the listener having different velocities. Okay, so that is done. Then 6.2.1 for questions this, we must state A, B, C for each. Okay, so where is the source stationary? Okay, I think it's option A because there's no change. We're not seeing this decrease or the increase and so on. So A, source is stationary. So when is the source moving away from the observer? So when you're moving away from the observer, what happens? The wave increases. So I'll go for C. And then you must give a reason for 6.2. 22. So the frequency, okay, saying the frequency decreases, or you can tell us that the wavelength increases, because this point will be the source. So this distance is increasing. So the wavelength increases, the frequency is decreasing. Then 6.3, they're telling us that if an ambulance that is moving right from the observer at this speed, and the frequency of the siren that is heard is at this frequency. I feel the frequency of the observer with the speed of air is that an ambulance is moving away. So one thing we know about the Doppler formula is that the frequency of the listener is equal to V plus minus V of the listener over V plus minus velocity of the source times the frequency of the source. Now, since the ambulance is moving away and the listener is stationary, okay, moving away from one side at the speed. So that's 340 over 340 minus. Is it going to be minus or a plus? Because an ambulance is moving away from one side at this speed. Also, this has to be a plus, so that we have a smaller object. Then multiply by the frequency of this source, which is 900. Okay, so 340 over 340 plus 25 times the 900, we get to 838.36. 838.36 hertz. Okay, then the hydrogen spectrum line from the sun has a wavelength of this. The spectrum line of the nearby star has a wavelength of 657. What can we consider about the relation of the star in relation to the sun? Okay, so we can see that the wavelength of the spectrum lines of the hydrogen atom from the star is longer. Okay, the wavelength is longer because this is 656, this is 657. So the star has a longer wavelength than the hydrogen atom of the sun. So which means this is going to be the red shift, and this simply means the star is moving away from the sun. Okay, question number 7. Question number 7. An investigation was carried out to show how electric field varies at this distance with positivity charge, positively charged field. To achieve this, positive charge Q was varied and so on. So the following table, so you have the charge in nanocoulomb and then the electric field. Okay, then define the term electric field at a point. So this is the force. Okay, the force that is experienced at a unit positive charge at a point. When you check out the videos of electrostatics, you get that definition or the definitions. Then they want us to draw the electric pattern for positively charged. So when it is positively charged, we expect the field lines to be moving out. Okay. Remember, these field lines should never cross. So that is that. And then 7.3, they want us to plot a graph of E versus Q. With the graph E versus Q. So I'll just try to put that sketch. There's a graph page. Let's say 1, 2, 3. I'm just gonna use 2, 4, 6, 8, 10, and so on. Then here I can use terms. It makes sense. 10, 20, 30, 40, 50, and so on. So we know that 1 is with a 4, which is somewhere there. And then 4 is going with 16, which is slightly below. And then 8, this is 8. It's going to go with 42. It's slightly above. 14 or 11 is slightly above 40 there. And so on. So just plot the points, but you're going to notice that these points are not forming like a normal straight line. So it means you need to draw a line of best fit, a line where all the points are close to that line. Okay, all the points may not pass through the line, but all the points must be close to the line. So that is the graph that will be needed for you to get the formats. And then you need to use the graph only to answer the question. Identify the controlled variable. So in this case, the controlled variable, if you have to look at the graph, remember it is the E versus the Q. Okay, E versus the Q. Now it's the other way. This is the Q versus the E, okay, E versus the Q. So the only thing that is controlled here, because they said the distance is varied from the distance away from the positive charge, fixed distance. So that is the controlled variable. So the distance. Okay. And then the dependent is the E, the electric field. Remember, in any graph, whatever appears on the y-axis becomes the dependent. The x-axis, the horizontal, is always independent. And then determine the fixed distance between the charges. So in this case, we can find the gradient, which gradient will be the E over the Q. Remember from our E, K, Q over R squared. So which means this gradient must be equal to K over R squared. That's what I'm seeing from this formula. If I can get B over Q, which is the gradient, then I have that. So we need to find the gradient. So with the gradient, we can find, I don't know, we can use the gradient, so we can even just gradient with this graph of mine that's not accurate. It's going to be a bit weird. But no, it's fine. We can get any points. Let's say I'm using the first point and then the last point. Okay. First point and then the last point. Okay, so I'll try to use my first and last values, okay, to get the gradient. So that's going to be 55 minus 4 over 14 minus 1. This must be equal to K, which is 9 times 10 to the 9 over R squared. Okay, so 55, okay, which is going to be a 51 over 15. When I do my cross multiplication, that's going to be 51 R squared is equal to 9 times 10 to the 9 times 13. So R is going to be the square root of 9 times 10 to the 9 times 13 over 51. Let's see, 9 times 10 to the 9 times 13 over 51. And 13 higher becomes 1. Did you do the correct things? Because it's going to want us. it's going to contrast. I'm getting 4, 7, 8, 9, 6, 4, 9, 4, 8. Let's go back to the graph and see. Because this was the nanocoulombs. Okay. And then this is a K, which is like a Q. Okay, we can now see. So nano and kilo. So the Q is times 10 to the negative 9. And then this is times 10 to the third Q. So when I simplify that, okay, I should change a whole lot of things to sum that. It's gonna give me now the 51 times 10 cubed. But why am I doing that? Just say 10 cubed. And then this is times 10 to the negative 9. Let me just include it there. Times 10 to the negative 9. And then times 10 cubed. Yeah, perfect. So I'm getting 0.04789. I'll just make it 9 meters. Perfect. So guys, that's the answer. Then question 8, a battery in the circuit below has an EMF of 6 and internal resistance of that. With S1 and S2 open, can we give the reading on V2? Where is V2? This is V2. So V2 is connecting the EMF, which has to be 6 volts. Okay, it's connecting to the battery. Then with S1 closed, if this is closed, it means the current is now taking this route, passing through R and then this. They're telling us that the reading that was recorded is 0.75 for the ammeter. Explain the meaning of this. Okay, so in a charge of 0.751, I don't know, are they asking us to explain what current is? Okay, so you can say the charge of 0.75 coulomb traveling in 1 step out, because that's what current is. Then with S1 closed, we want us to calculate the internal resistance. Okay, so we can use the EMF formula. Okay, which EMF is I into R plus small r. We now know the current is 0.75. Our EMF was a 6, 0.75. Do we know the external resistance? No, that's what they want us to reach. The internal resistance, they give us a 0.4. Divide both sides by 0.75. 6 divided by 0.75, I'm getting 8. And then 8, I subtract 0.4, I'm getting 7.6. Okay, same divide. 8 minus 0.4 will get that. So 7.6 ohms. Then they want us to get the value of R. Now remember, with capital R, still S1 is closed on. With this capital R, it's more like a parallel combination. So what I'm going to do, I'm going to combine. Let me just write it in. So I'm combining this and that. So let me combine the 3 and the 1 to give me 4, so that I have R and then a 4 1. Okay. These combined together must give us the 7.6 ohms. Since it's parallel, I can use the product and sum. So product over the sum is giving me the 7.6 ohms. My product is going to be 4R over 4 plus R must give us 7.6 ohms. If I try to cross multiply 7.6 times 4, I'm getting 30.4 plus 7.6 r must give us 4 r. Is the product over the same? Why am I getting something different? Is it going to make sense? 7.6 minus 4 is 3.6. 30 divided by the answer, you get to 8 or something, which doesn't make sense. Let me see. Oh, sorry guys, sorry. We also have another 4 ohm. There's another 4 ohm there. We are such honestly. Otherwise, not making sense. So let's see. So we have we said product over the 4 plus r. Now plus this 4 ohms must give us the 7.6. Move the 4 that side. 4r over 4 plus r must give us the 3.6. Cross multiply 3.6 times 4, I'm getting 14.4 plus 3.6 r. When I move the 3.6 that side, I'm going to end up with 0.4 r is equal to 14.4. Divide by 0.4, divide by 0.4. So my r is going to be 36 ohms. So this r is a 36. So what I did, I first combined these two systems in series directly and got the 4 ohms. And then since these are two resistors in parallel, I say the product over the sum, we give you the effective resistance of just the parallel combination. Okay. Alternatively, what someone can do, if you can have the 7.6, okay, we subtract this 4, then I'll be left with 3.6. So which means this parallel combination is equivalent to just 3.6. Okay, makes sense. Then 8.4 S1 is now open and S2 is closed. How will the power dissipated by the 4 ohm change? Okay. So if this is open and this is closed, which means the power will just take this switch. Remember, this whole thing is a 3.6 ohms combined. This is a 4 ohm. Now, if this is off, which means we only have 4 ohms within the circuit. So the total resistance will be 4 ohm, and then that internal resistance, which is always a must. So one thing we have to do, we have to say that the resistance is going to increase. That is for the fact. Okay, it will increase because the external resistance has decreased. Okay, so the power, we're saying the power increases because the external resistance has decreased. Then you can tell us, so you can use the formula of power being directly proportional to I squared R. Okay. Then 8. They are telling us that the 12 learners conducted an investigation to determine the internal resistance of the battery, the circuit below is that. Okay. And then a graph was plotted. From the graph, can we deduce the EMF? So EMF is basically where the graph normally starts, as long as this potential difference against the current. So this graph is starting from 4.5. So the y-intercept, that is the EMF. Then calculate the internal resistance there. So internal resistance will always be the gradient of this graph. The gradient, because if this is E, potential difference in the current from EMF is equal to pi r. If we get the EMF over the current, we end up with kind of resistance. So the gradient, so we consider the change from there up to there is going to be 4.5 negative. Because I'm getting with negative or positive. So whichever you look at it, you can have 4.5 to 0 minus 4.5, which is negative 4.5. Then I'm dividing it by from 0 to 7.5, which is positive. So I'm going to get a negative answer. Why? Because when you consider this line is having a negative gradient. So it's negative 4.5 divided by 7.5, that's giving me negative 0.6. So which means our internal resistance is 0.600. Question number 9. Study diagram below and answer the questions that follow. So what type of generator is shown in the diagram? You must motivate to answer by referring to the specific names of the components. Okay, so this has to be, we have this and this, and then we are calling it a generator. So it's an AC generator. Okay, number one, it has just reference. That's number one. And then number two, it has a handle, which handle will be turned for you. Okay. So if it was connected to, let's say, power supply or something, then it would definitely reduce it. Then indicate the direction in which the current will flow in section A. So since we see the field to move in this direction, we want us to get the current. So using the correct right-hand rule or the correct hand rule, we can see that it's moving that direction. So it's going to be B to A. It's going to be B to A. And the 9.3, the following graph was obtained from the generator. How many rotations are we having? So we see that from here up to here. Does that make sense? No, from here up to here. That's one rotation. Okay, the trough, and then next one rotation, and then this is a half. So we can say that it is 1.5 rotations, or 1.5 times. And then they want us to define root mean square, RMS. Okay, so root mean square current is saying that is the alternating current, which produces the same amount of energy as the equivalent of the DC. This is saying is the AC current that produces AC current, which dissipates, or we can produces same amount of energy. And amount of energy as the DC. Then calculate the average power. So with average power, remember we need to know the maximum power. Okay, so if we have I RMS, we shall get our I max divided by the square root of 2. And we know that power can be given as I squared R. Okay, we have the resistance, or we need the current. In the question, they told us what is going on. And you can see from the graph that the current is 15. So what we're going to say, we're going to convert this maximum current, which is 15, over the square root of 2. I'm going to square this, and then I'm going to multiply it by the equation. So we say 15 over square root of 2 squared times the 30. That's giving me 3375 watts directly. So if you have decimals, because of doing this separately and rounding it off, no problem, but the answer should be close to the same. The 9.4 is a hair dryer, not a chair dryer. A hair dryer that is rated at 2.2 watts. Okay. At 240 volts. Then assume that the hair dryer is secure resistor, that is the maximum current that flows through the hair. So what we can see then is that we have the power. Okay, so we know that. Let me just use a different color. Okay, the P average is I times P. Now, what is our power? It's 2.2. What is our current? What is our current? Our current, we don't know, but we have the voltage, which is 240. So I'm just going to say 240I. Then when I divide 2.2 by 240, I'm getting 9.16. 9.1667 amps. Question wants the maximum current. So for us to get the maximum current, you must get the IRMS times the square root of 2, which means my answer of 9.167 times the square root of 2, I'm getting 12.196 amps. That is 9.5. Then question 10. Diagram below shows a photo tube that was used to demonstrate the photoelectric effect. Demonstration was carried out by shining a light from the red, green, ultraviolet into the surface. Okay, they gave us the demonstration number, the color of the light, and then the emitter ring. Okay. Can we explain what is meant by photoelectric effect? So we know that this is just a process by which electrons, okay, so electrons are ejected. And so electrons are ejected from a metal surface. From a metal surface after a light of sufficient frequency, and a suitable frequency is incident on the surface. So in other words, you first shine the light on the surface, and then electrons will come off, but the light has to have sufficient energy. And then explain why there's no reading on the emitter when the red light is shown on. So we know that for red light not to show, we know that the frequency is low. Okay, so the frequency of the red light is lower. The frequency of the red light is lower than the minimum, which minimum is normally known as the threshold, the minimum frequency needed. Then for the following statements, use increase, decrease, and so on. So the kinetic energy of the photoelectrons dash when an ultraviolet is shown in the surface. So in this case, we're just going to say increase. Okay, in ultraviolet, and the reading is a yes, so it increases. Then the reading on the emitter dash when the green light. So green light is also a yes of higher intensity. Explain the observation. So since the ammeter reading is a yes, which means this increases also. Ammeter reading increases in the green light use of higher intensity shown. We need to explain that. Okay. So what you need to know is that with intensity increases the number of electrons, or the number of photons, not electrons. So the number of photons will increase by unit time. Okay, so if the number of electrons are increased by unit time, which means the rate at which they will be striking the metal surface is going to increase. Hence, the number of electrons that are leaving the surface will also increase. Then 10.4, they're telling us that the cathode is made up of copper with a work function of this. Okay, so which means W naught is 3.52 times 10 to the negative 19 joules. If ultraviolet with a wavelength of 390 times 10 to the negative 9 meters was used during demonstration, calculate the speed. They want us to take the beat. Now we know that E, the energy, must be equal to W naught plus the EK max. Okay. So this E can be given as H lambda over C is equal to our W naught. Plus we can still take the EK max and then we can do the substitution. So the value of H is always 6.63 times 10 to the negative 35 in this table. Times the wavelength, which is 390 for the seed 390 M. Why am I saying wavelength? I think I've messed up this formula. Let me just confirm it's HC over lambda. Sorry guys, about it. It's HC over lambda. HC over lambda. So 3 times 10 to the positive 8 over now the 390 times 10 to the negative 9, since it was number. This must be equal to the work function that they gave us. Its work function was 3.52 times 10 to the negative 19 plus my EK max, which I don't know right now, but I'll sort it out. Let me first figure out what is this and that. So I'm going to move this to the side. Okay, so I have 6.63 times 10 to the negative 34, that's 7. Okay, I'm multiplying it by 3 times 10 to the 8, that's the speed of light, over 390 times 10 to the negative 9. Okay, I'm subtracting 3.5 times 10 times 7 to the negative 19. So I'm getting 16 times 10 to the negative 10. Now I know that E max is a half times the mass of the electron, which is 9.11 times 10. 9.11 times 10 to the watts. What is electron mass? Negative 31. Okay, so negative 31 V squared. Now I'm going to divide both sides by that. So divide by 0.5 times 9.11 times 10 to the number 2, 31. Well, getting a big answer. It's really big. It's really big. Okay, but I need to find the square root of the answer. Square root of the answer, which is the velocity, is giving me still a big answer. Okay, so if I find I'm getting 5, 9, 2, 6, 7, 3, 10, 9, 7, 1, 2, 3, 4, 5. So it's 5.9 times 10 to the 5. That's what I'm getting without the rounding offs and stuff. This is what I'm getting.